Hello, my name is Jordan Sass, and I will be talking about what I've been working on for my master's thesis. My original recording for the defense had some issues with it, so I am re-recording and I'm going to talk about what I've been working on for the last 2 years. Of course, it's my master's thesis, so this is going to be a little bit of a clunky explanation, but the purpose of this recording is to introduce the topic and as a shareable explanative of what I've been working on. So without further ado, the double pivot network simplex method. So who am I? I am a current master's student at UNO, but I got my bachelor's in mathematics with a minor in computer science in 2022, and I specialize in OR. All I do is study and write lecture notes of OR. I took in every single class, and I even taught dynamic programming last semester. I work as an IT technician, and I specialize around a lot of networking infrastructure, computer programming, and IT ethics. Thus, it's no surprise I am into network optimization. So the outline of this thesis is we're going to talk about minimum cost network flow problems and the network simplex method, which I'll call the single pivoting method because it's a mouthful. I'll summarize the single pivoting method, and we'll talk about the extended threaded index method, also known as the XTI method. We're going to talk about block pivoting, and then we're going to talk about the double pivot network simplex method, and then summarize the implementation of it, and then computational study and results and in future work. Without further ado, the minimum cost network flow problem can be represented as a graph where n denotes a set of nodes and a represents a set of arcs. And the goal of the minimum cost network flow problem is to minimize the cost of positive flow amongst all arcs in the graph, subject to the balance in and balance out constraints. And of course, we have bounds on each of these arcs, in which we have the lowest bound being 0 and the upper bound being a set fixed value. So an example of this, suppose there exists 6 warehouses with several delivery trucks, where the warehouses are the circles, which are called nodes, and the arrows that connect the warehouses, roads, have an upper bound and a cost, which is shown to the right. And the curly braces above each of these nodes represent the balance of demand versus supply. Demand has negative values, supply has non-negative values. And how could we solve minimum cost network flow problems of this form? Well, we could do 2 ways. We can put it into this linear form and then solve it with the simplex method, or we can investigate other ways. And before we even actually start getting into that, we should actually probably talk about real world applications in which this appears, in which we need better solvers than just putting it into a linear program. So there's currently solving money distributions in Kilgate, Sri Lanka. Kigali, so Sri Lanka, sorry. And then inventory transshipment and airplane cargo management. So if you ever ordered anything off at Amazon or any other shipping facility and had your packages shipped overseas, it's probably been minimized in such a way that the package gets to you on time in the most minimal number of transfers, and that's what that study did. And then there's emergency fleet management in disastrous situations. So if you have road closings, if you had obstacles on the streets, how could we put emergency vehicles on the roads in such a way that it gets to their destinations in the minimum number of roads needed? And then there's RNA structure position prediction, which is beyond me, but matching DNA and RNA. And then there's optimizing fire emergency routes. So if you have coal mines that break out in fires, what's the minimum paths needed to have them escape the said mines? Anywho, these are very, very large problems, and putting in the linear programs isn't fast enough. Therefore, we need to find some other solution methods. Thus, how do we solve these? Well, one method is the single pivot network simplex method. And it was originally created in 1956 by George Danzig to solve transportation problems. And it was much faster than the simplex method in that it didn't need to calculate B inverse and do all this complex vector optimizations, operations, to traverse from one extreme point to another. It preserves the graph theoretical aspects of the original problem, and it does this by solving using a spanning tree basis. So how do we create this basis? Well, what we do is we introduce a artificial node. So like for the warehouse problem, we introduce a node 7. And what we do is we add arcs from each original node to this artificial node. If the balance is greater than 0, it's pointing toward it. If the balance is less than 0, it's pointing away from it. And it's basically an initial solution for the single pivoting method to improve. So how does it prove from one solution to another? Well, what we do is we calculate all the dual variables of all the nodes because each node has associated dual problem. And what we solve this by arbitrarily picking a node to have a root value of 0. Traditionally, we make this a root node, and then we take that fixed value and solve down all the tree. And then we calculate the reduced cost of all arcs not in the tree. So all the what we call non-basic and basic arcs. Basic arcs are arcs within the tree, non-basic arcs are arcs not in the spanning tree solution. And we calculate the reduced cost taking all these dual variables. And we pick the most improving reduced cost of a non-basic arc if it's lower bound. That means that its flow value is fixed to the bottom. Or we take the least reduced cost if the non-basic arc is on upper bound of its upper bound. And then we introduce the improving arc into the spanning tree to induce a cycle. And an example of this is the following. If 7-11 is entering here, then 11 and 10 is against the flow cycle, and 10 and 13 is with it. And what we do is we calculate the minimum direction, the minimum arc based on this direction for all arcs in the cycle, and the most minimum arc leaves, well, to counteract the effect of entering an arc. To summarize the single pivot network simplex method, what we do is we calculate the dual variables of the nodes in the spanning tree. Then we calculate the reduced costs, and then while there's an improving reduced cost, enter it, generate the cycle, and find the minimum, and then recalculate the dual variables via the XTI method and recalculate the reduced costs. So you might be asking, what is the XTI method? And that actually is a question of how could we make the single pivot network simplex method computationally more efficient? It's already more efficient than the single pivot, the traditional single pivot method, but how can we make it computationally more efficient? How can we squeeze more power out of it? Well, we could do this by manipulating how the data is stored in the initial spanning tree solution is stored within the pivoting method. So the single pivot method was, the XTI method was created by Barr, Glover, and Klingman in 1979 to improve the overall CPU runtime of updating the spanning tree solution. What this means is they introduced a bunch of list functions and lists that store data about the tree in the most minimum but fast way. So P of I is a list function that calls upon a list that asks what is a logical predecessor of a node. And then S of I is a list function that asks, including the node itself, how many children nodes are attached to it. E of I is the bottom most right, deepest depth ending node of the subtree rooted at node I. And then T of I is a threaded successor of node I, ignoring depth. If I were to flatten the tree, what is the next node? And the following notation was augmented for the thesis, my thesis, but only one of them was new that I introduced. The other one, reverse thread, I improved for my implementation by, instead of doing what Barr et al. Wanted to do, was do a procedure that went through the entire threaded index and then went backwards one once you find the thread you want to do reverse thread. I instead represent it as a list and list function and update it and maintained it that way. But I introduced a new list and list function called direction. So if you keep in mind about the predecessor, which I'll explain more in a bit, you ask the graph if the predecessor of a particular node I, if the arc is contained in a way that is it pointing toward the root node, then you return true. If it's not, if the arc is pointing away from the root node, it's false, or it's 0 if it's the root node. So what does this all allow us to do? The XTI method allows for fast cycle discovery and construction. It allows for us to also update dual variables and maintain the tree in the most minimum number of steps. Step 1 is we remove the leaving arc from the spanning tree to create 2 subtrees. Then step 2 is determine the smallest subtree. Step 3 is reverse the small subtree and update the node potentials of that subtree. And then step 4 is reattaching that subtree. So an example of this is as follows. The extended threaded index method allows us to enter an arc. And then when we enter an arc, we can ask, hey, how many successors does each of these nodes have? Well, 7 has 1 and 11 has 1. Is 7 equal to 11? No. Then follow both of their predecessors' paths up. Hey, is 5 has 3 successors and 10 has 3 successors, but does 5 equal 10? No. Go up the predecessor path. And ask the same question again, and it'll get the same result, and we go up one more time. And then 1 has all 12 nodes, and 4 only has 5 nodes, so only goes up the 4 path. And then ask the question again, and 1 does equal 1, and it has all 12 nodes. Therefore, we found the cycle 7 to 11, 5, 10, 2, 13, 1, 4, and then the intersection 1. And then if you are computationally efficient, you would determine the minimum at the same time, which the minimum here was 2 and 1. Now that we know the minimum and we found the cycle, we can actually update the tree based on splitting it based on that leaving arc. So if we leave that arc, then we have the tree rooted at 2 and the tree rooted at 1. And the cool thing about this is we can actually update all the dual variables based on the reduced cost of the entering arc. If the entering arc is pointing to the smallest subtree, although that we want to update, we add that to all. Otherwise, we subtract all. And again, this method aims to update the subtree in the least number of calculations. So what it does is it asks here, which one's the smallest subtree based on successors? Well, here it's the tree rooted at 2. Therefore, the tree rooted at 2 will be reversed and attached to the bigger tree and have all its dual variables updated. And that's what happens. It traverses up 7, 5, and 2 and reverses the tree. And we get the following, and then it reattaches it based on the entering arc. So that's one method of updating and computationally speeding up the problem. Another method is block pivoting. So what we need to do is instead of calculating all the reduced costs of all the possible entering arcs, we need to calculate only ones within certain indices. So calculating the reduced cost of all arcs is time consuming. It is very, very time consuming. So I implemented block pivoting to reduce the number of arcs needed to calculate per block iteration. Sorry. So block pivoting calculates the reduced costs of only a certain number of arcs within a block based on location indices. It puts indices between a whole list of arcs and then only proceeds to calculate those within the indices, and then it moves on in chunks until it finds an arc. And if it can't go through all the possible chunks and finds an arc, it terminates the program. And Curley and Kovacs determined in their research paper, which is in 7, that the best possible block size you could use for the network simplex method, the single pivoting method, is one where the square root of m, where m is the number of arcs in the problem. So now that we know the single pivoting method and computationally effective ways to update it, what if we pivoted 2 arcs instead of 1 per iteration? That's the meat and bones of what my thesis is what if we decided to improve this computationally in a different aspect in multidimensional search. So the double pivot method enters 2 arcs per iteration into a spanning tree to induce 2 separate cycles. These cycles have a chance to overlap, and if they do overlap, then there's a lot of questions need to be asked, like what's the acceptable leaving conditions for arcs, what arcs can leave, and what is acceptable change of flow. So the acceptable leaving arcs for this overlapping case is as follows. Using this example graph, where blue denotes cycle 1 and orange denotes cycle 2 and magenta's overlap, we need to ask ourselves, if we enter 2 arcs, what arcs are allowed to leave? Well, here's a case. What if 310, the only overlapping arc, leaves? Well, this is not valid because now our spanning tree solution became just a normal graph. It's no longer a tree. And part of the network simplex method requires it to be a tree. So therefore, it's not valid. And again, what if we only leave 1, 3, and 310, the 2 overlapping arcs? Well, we get an isolated tree. It's still not a spanning tree. Therefore, this is not valid. What if we did 1 overlapping arc and 1 non-overlapping arc in either one of the cycles? Well, this is actually valid, and you could do this, and this will always guarantee that you leave a spanning tree. How about 2 non-overlapping arcs? Well, that's also valid, and you also get a spanning tree solution. Therefore, the only 2 situations that we can enter 2 arcs and leave 2 arcs is 1 overlapping and 1 non-overlapping, or 2 non-overlapping. And now that we found the acceptable leaving conditions, we need to find ways to update this in a efficient way. So what I did for my thesis was I introduced 2 new notations called overlap and flow direction for cycle 1 and cycle 2. So what the overlap list function and list does is it asks during cycle construction if a node I is in cycle 1 or if a node I is in cycle 2, which it adds 1 and 2 respectively. So you get the following conundrum, the following presentation, sorry, where you get 0 is if I call upon a node I and I get 0, it means it's in no cycle. If I get 1, it's only in cycle 1. If I get 2, it's only in cycle 2. If I get 3, it's in both cycles. And additionally, using this, I can call upon and ask, hey, is the arc associated with this against or with the flow direction? And if it is an against, I can have it in C1 and C2 here respectively, and immediately know flow direction for every single possible arc, which is very fast and efficient. So now how do we determine the change of flow that we know, since we know all this information? Well, what we're going to need to do is we're going to need to construct two variable programs determining if both cycles are with each other in the direction of flow or against each other. If they're with each other, then we're trying to maximize the reduced cost of entering arc cycle 1 and entering arc of cycle 2, C1 and C2 respectively, subject to the most minimum overlapping arc and subject to the most minimum non-overlapping arc of cycle 1 and subject to the most minimum non-overlapping arc of cycle 2. Because again, the acceptable change of flows is denoted on the most minimum arcs. And one thing I noticed here for the problem was if you standardize this, you can actually deploy vertex-enumeration to solve this, because what determines what arcs leaves is based on if the slack for that arc is 0. So you might be asking, why don't I just call the simplex method to solve this instead of doing this vertex enumeration that I mentioned? Well, it is time consuming. It is time consuming to call the simplex method and rely on it calculating basis inverse and all the vector calculations. I need something faster to call per iteration. The whole point of this, the whole point of me exploring this, is to do this faster than the single pivoting method and do it in the most efficient way possible. And there exists other methods to solve two variable problems. The original double pivot simplex method that I got this idea from used to solve two variable problems to determine what basic variables enter and leave the basis. The cool thing about my problem, unlike that problem, is my constraint coefficients are very simple. It's much easier to solve this via brute force. Therefore, I'm going to deploy vertex enumeration, and in general, for like unclosed polyhedra, it's NP hard, but it's traditionally a hard problem. But this case, it's actually very simple, and you could do it by hand. And I would normally have to have an animation for this, but this is PDF. But what I did was I modeled this and then solved it for every single possible constraint. So S1 here corresponds to the overlapping arc, and the X1 arc, minimum arc, leaves the basis. S2 is X1 and X2 leave the basis. S3 is X2 and overlapping leave the basis. S4 and S5 are overlapping, leaving the basis. The astute might notice that I don't include the extreme points here of cycle X1 and X2 or the origin. Well, the origin makes sense. Why would I do all this computational work for nothing? But the extreme points for X1 and X2 correspond to single pivoting. Why would I do all this work to effectively single pivot? The whole point of this is to double pivot, or at the very worst, exchange the overlapping arc out to aggravate the basis further. Because the whole point is to aggravate the basis as much as possible to get to the ending solution sooner. And what I do is I calculate all these values based on certain conditions. And if those conditions are true, you get the value, else you get negative infinity. And then I argmax each of these conditions such that if I get a tie, I can control which values in the tie precedes other values. I'd rather in a complete tie have two overlapping arcs leave the basis and aggravate the solution further than having the S4 and S5 case happen, and it's only one arc. Likewise, for the mixed flow case, I do the exact same thing, except we have the conundrum of if both cycles are against each other, there's a possibility of one hitting the upper bound sooner than the lower bound is hit. Therefore, each overlapping arc needs to be split into two separate constraints. And the same logic as follows, and the same recourse applies in that you have all these values that correspond to overlapping and non-overlapping arcs, and it determines the leave conditions for arcs. So to summarize, to implement this, you just need to calculate the dual variables, calculate the reduced costs. While there's an improving arc, arcs, it's possible you only get one arc in a certain iteration. If you do that, just single pivot in and out that cycle. Enter the arcs with the most improving reduced costs. Generate cycle 1 and cycle 2 if possible. If there's only one cycle, then a single pivot. Else check for overlap. If there's no overlap, it's effectively possible to just double single pivot those arcs respectively. That means just enter two arcs and leave two arcs using single pivoting methods as you would. If there is no overlap, then do the flow change procedures as described, and then recalculate the dual variables sequentially at the XGI method, and then recalculate the dual costs. Now, computationally, is this faster? Well, that's what I needed a benchmark, and that's what I did. So the NetGen benchmarking library instances from Kovac's web library was used to test iteration count and CPU runtimes of both methods. And the following was benchmark: iteration count and types, CPU runtimes, alpha testing for the block sizes, which I found that through extensive testing that any value for alpha between 1.7 and 2.3, with alpha being in the median 2, was the best for the double pivoting method, where alpha is taken times the square root of m. And so 2 times square root of m, where m is the number of arcs in the problem, was the best for the double pivoting method. The NetGen library is full of 70 problems, which is actually denoted or categorized by instances. So there's NetGen 8, 9, 10, 11, 12, all the way to 22, and it doubles in size. But NetGen 8 has 5 problems, A through E, 9 has A through E, so forth, for a total of 70 problems. The smaller problems are the NetGen 8, 9, 10, 11, 12, and then it gets to medium problem 13, 14, 15, 16, then larger problem 17 through 22. So what was found was that the single pivot outperformed the double pivot in smaller problems. And as you go ahead and work to the medium-sized problems, the double pivot starts to equal and starts to beat the single pivot. And as we keep going, it keeps this lead and it keeps this lead. And then when you get to larger problems, it starts getting really close to single pivot again, but it keeps its computational lead. However, NetGen 22 was inconclusive because I had set a 40-hour, 8-hour computation threshold, and both methods hit that threshold every single time in that benchmark. So therefore, there's not enough conclusive data from 22. Again, I tested this on my laptop, and my laptop wasn't computationally effective for these larger problems. So the pivot type for the double pivot network simplex method is as follows. Single pivot means you only enter and exit one arc. Double single pivot is you enter 2 arcs and leave 2 arcs, and there's no overlap. Double pivot is to enter 2 arcs, leave 2 arcs, but there is overlap. A false double pivot is you enter 2 arcs, but only one of them can leave the basis. So therefore, you try to enter 2, you can only enter 1, and only the overlapping leaves. It's effectively a single pivot with more steps. But was found that was that globally, the double pivot network simplex method did outperform the simplex method, single pivot method, by approximately 50%. And that is expected, and that is good news, because that means I implemented an algorithm that did what it was promised, was to enter 2 arcs, leave 2 arcs, and try to solve problems in 50% the computation time. Now, an interesting thing is false pivoting. So for the total amount of problems for NetGen 8, 32% of the problems on average had false pivot, iterations had false pivots. While NetGen 22, only like 1% of it. For the one I could solve, which was problem A, I was able to solve all problems, including NetGen 22, with iteration because it had no upper time limit. I let it solve and it took weeks. But what was found was for larger problems, as you got larger, the number of false pivots decrease. And I believe for the smaller problems that this is why the double pivoting method was slower than the single pivoting method. Was it did all this extra work for nothing. It did all this computational stuff for nothing. So the double pivot outperformed the single pivot method by over 5% in CPU runtime, like in total, on average, and gained an advantage towards the larger problems where were outperformed by 12% on average. Therefore, the double pivoting method should only be used to solve very large problems over the single pivoting method, which should be used for smaller problems. It's effectively overkill to use a double pivoting method on smaller problems, which makes sense. Future work of this method includes parallelization of the multi-single pivots, since the XTI method makes cycle construction and determining overlap extremely cheap. And split it, so that's basically me saying that if you have an iteration and you have all these arcs, you can enter all these arcs and then just look through every single entered arc and pick out only the combination of one of them, like the maximum combination of them that do not overlap, and single pivot those. In addition, since this is a multi-dimensional method, splitting the XTI method into multiple number trees needs to be investigated to avoid the sequential XTI method procedure that I did, because I could probably make this even faster if I came up with a method that, instead of splitting it into one tree, splitting it into 2 trees, 3 trees, 4 trees, so on. And further benchmarking of both methods with different pivoting rules. It's possible that the double pivoting method could be performed better with alternate canning list, first pivoting rule, first arc rule, best arc rule, probably not that. But some other pivoting rules could probably make the double pivot method even more computationally efficient. And then this begs the question, triple pivoting, quadruple pivoting, quintuple, and double pivoting. If double pivoting is possible, is triple pivoting, and so on, which triple pivoting, I can tell you right now, is possible. I've already done work and research on that and effectively proved it. I just need to write it up. But yes, this is completely possible and is computationally effective. A question this asks and proposes forth is, at which point does we get diminishing returns? Do we get diminishing returns at quintuple pivotings, sextuple pivoting, 7 pivoting? Who knows, but that's research that needs to be explored. The following was reference that was used for this thesis. And that concludes this presentation. Thank you for listening, and if you have any questions, feel free to reach out via to my email, which I'll link below. Thank you.